my paper is a case study that's looking at the differences between a bionic hand and what's called a body-powered prosthetic hand in a highly demanding work environment. Which I think is really cool because I really like prosthetics. I think they're neat. So just a briefer on what prosthetics hands are. You've probably seen them before because they're kind of like everywhere in science fiction media, especially fantasy. Like there's a ton of characters that are missing an arm and they replace it with some sort of metal prosthetic where they're controlling it with their mind, which we'll call neural control. Nowadays we don't have the technology to like directly implant an arm into someone and have it work with their mind controlling it. We do though have sort of an alternative with these fancy bionic hands you might have seen around. Now the way these are controlled is with myoelectric control. For all intents and purposes nowadays, whenever anyone brings up neural control in regards to prosthetics, they're probably talking about myoelectric. Now, myoelectric's a big word, but myo just means muscle, so it's muscle electric control, which basically means that we've got our hand, and then if you look at an arm, right, you can place an electrode on someone's arm and you can measure what's called electrical signals that come from these muscles. Now, the cool part about this is if you move your hand, you'll get a muscle signal just all along the arm because your muscles aren't just like apart from each other. They're all connected in sequence. So with these prosthetic hands, they put a fancy socket on someone's upper arm if they're missing their elbow or the lower arm if they're missing their hand. And they can use these electrodes to try to track the idea of muscle movements. So if you want to move your hand, you can even feel it. It'll make muscle movements. So they just kind of map these muscle movements in other muscle systems to what a hand movement would be. And that's how you get kind of cool stuff where you can like open and control the hands with kind of your thoughts. Hence neural control. Now, the other alternative, which we've been using for a long time, these were invented in 1912, are what's called body-powered split hooks. The way they work is you've got these cables that run along the arms. So as you move your upper body, it tensions the cable and it causes this split hook to open and close. These are pretty much the standard just because of how durable they are and they're pretty ubiquitous. In fact, they're the prosthetic that's mainly used in most workplaces, especially because upper arm amputees are predominantly in blue-collar jobs. And these types of prosthetics have been designed to kind of handle similar stuff. They do require a range of dexterity, which you can get with these hooks. They're just not as dexterous as your fingers. Most of these involve heavy work, and as a result have high rates of abandonment because these don't necessarily work as well as just using whatever's. This cool part about this photo, this I actually found on a woodworking forum. So it just kind of goes to show that these are being used and what we'd associate with blue-collar jobs. Now, this study, you looked at both myoelectric hands and body-powered hands. So for the myoelectric hand, they use this iLim Revolution, which is the photo I've been using this whole time. And then for the body-powered hand, it was actually custom designed, which we'll get into. But they used a couple of different hands. They used the split hook. They used a Becker hand, which they don't really talk about in this study, but it was there. And then they used what's called an adult prehensor, which is like this claw. It was a case study, so there's only one participant, and it's actually the first author, which is kind of fun. I was like looking at the ethics, and it's like, yeah, so the person is the guy who wrote it. And that's kind of neat. So the first thing they did though is they tested the grip strength of all these different devices, because if you're looking at a hand, you want to be able to grab stuff. That's the point of it. So the bionic hand had a 1.6 kilogram grip strength, the hook had a 5, and then this prehensor had 25. Device weight is also really important because we are attaching a device to somebody. So if it's too heavy, it's going to cause a lot of issues. The bionic hand was the heaviest. Then the hook was the lightest. And then somewhere in the middle, we had our prehensor. Now, the other important part is what they were defining as a highly demanding work environment. You all probably have an idea in mind of what this is. This study was forensic medicine. Which was kind of out of left field, but I thought it was sick because like it is a highly demanding work environment. And it's also the job that the first author's been working in for pretty much his entire life, hence why they picked this. It's also not really a work environment a lot of people talk about, despite it being highly intensive. Because there's a lot of different tasks that require either delicate work or just heavy lifting. Like specifically, they look a lot at undressing a body, which is exactly what it sounds like. And then turning and transporting a body, and then just like lab work. They even look into like typing and kind of other stuff that has nothing to do with forensic field work, which was really fun. And their measures, where they were kind of trying to compare between the two arms, was a lot of sweating, and then also this manual skill level. These were both pretty subjective. They defined massive sweating as wearing 2 layers, so a t-shirt and a long sleeve shirt, and then just looking visibly wet after about 30 minutes of doing something. And then the manual skill level was also subjective. They justified this by saying that their user was very experienced within these fields, so he could be considered an expert. And he basically rated these tasks he was doing on a scale of 1 to 10, with 10 being the most difficult with given the experience. So the first thing I want to look at is like sweat outcomes, especially when you're looking at like myoelectric control. This is a very big deal because, like I said before, there's sensors that are measuring electrical impulses in your muscles, which means they have to be able to read it. And what they found is that the electrodes didn't really work after 10 minutes of like work, like when the user got too sweaty. And you're like, why? It's because they're wearing a ton of layers to this prosthetic. So it's not just like on skin contact. There's layers. But they found after 10 minutes of light work, the electrodes didn't really work. And then after about 1.5 hours, they were sweating profusely, just in general, which not great. They also matched this. They also looked at like remote location, so whether or not the location was remote. They found that if it was remote, there was just 100% rate of there being sweat issues. And they did use, on all these charts I'm going to show up, they used chi-square, these regression models to generate their p-values. And with the remote versus non-remote, they found that that was statistically significant with a p-value of about 0.04. And then they also looked at whether or not undressing the body was necessary. And this one was interesting because it wasn't as like big of a jump as the remote location per se and some of the other stuff we'll be looking at. But if the body was naked, they sweated less because they didn't have to take all the clothing. I was like, cool. Like I said, wild stuff. Then they also wanted to look at kind of the scene that your forensic pathologist is going to rock up to. And they found that the skill level was definitely correlated with the kind of scenario that they were presented with. So these suspected homicides were the most tricky of these outcomes locations, whereas the rest of them kind of had like a much larger range of the skill level they perceived. They then looked at how this related to sweat, and it was pretty similar. All these manner of deaths data that they collected, they did find to be statistically significant, which cool. They also had some qualitative measures, namely overuse and asymmetry. He was a unilateral amputee, which meant that he only had one arm that had a prosthetic. So as a result, you can imagine that there's some weight difference between your two sides, which results in asymmetry. And this can cause problems, as you might imagine, with like your musculoskeletal system. So the bionic hand they found gave our users severe shoulder and neck pain just after 1 day of working. Whereas with the body-powered hand, they did get severe shoulder and neck pain, but it was as a result of using it over the course of several days, weeks up to a month. And they really only had 4 days per year where it was really painful. Next, the skin. We'll get into a little bit more in a second about why the bionic hand resulted in these blisters and rashes that the paper actually compares to electrical burns after just using it for one period of time. Whereas with the body powered, they found that with all the different layers underneath the socket, they did get a rapidly a friction rash, but it healed pretty quickly, and it was built up over time rather than just after one instance of using the device. And then for temperature, the bionic hand is electronics, so it did have issues with extreme temperature, whereas the cooling was completely mechanical, so they didn't find it failed at extreme temperatures. And that was kind of their more like qualitative measures. There were no like actual numbers associated with any of these. This was just observation based. So going back to kind of the blisters I was talking about, within the socket, they have these ridged electrodes that are put into it in order to measure these signals. The reason they're ridged is it provides better contact with the skin and allows you to get a better signal. The problem is when you have it on for long periods of time, that just rubs up and down against your skin, and it can cause these friction burns that are rather severe, especially when you compare it with a socket that does not have these implanted electrodes in it. Next, like I was saying before, the way these work is if you move your hand, you're also moving muscles up in your arm. The fun part about muscles, and especially in your arm, is that they're not just connected to your muscles in your arm, they're connected to your whole body. So what they were finding was whenever their user like moved his torso, like they namely talked about like sitting to standing or like bending over, it was also causing these electrical signals to appear in the arm, and the hand was just kind of moving like without the user wanting to move it. So that was a problem. And the body powered arm did not get off scot-free either. The components for this one were really hard to find, like especially commercially. And at the beginning, before he started modifying it, it took like 1 to 2 weeks to get parts in and to like have it fixed. So he just didn't have a prosthetic at that time. And then they were having a lot of issues with the cables snapping because they would snap after like a week of use because they weren't that strong. And he ended up having to custom build his entire prosthetic in order to make it work for him and his applications instead of just using kind of like an off-the-shelf device. And then as for physically demanding work, they discussed at length about how prosthetics, especially like upper arm ones, are not tested with heavy work in mind, despite that being the majority of people who need them. So they'll kind of gloss over a lot of like the heavy work implications when they're doing their testing, and they won't really look at like high sweaty environments because that's not ideal for like sensors to work and stuff. Even though that's kind of going to be the use case. And this results in a lot of people just abandoning the device, which is where they just don't use it anymore. They're given their myoelectric arm and they just go, no, don't like that. And then they don't touch it, even though it's, you know. Next, the studies that look at prosthetic arms also don't really look into like the job requirements, especially the participants. Like they'll say we had these participants, but they won't go into depth about the day-to-day work these people are doing. So there's all these, there's just like kind of this latent gap about physically demanding work in both the design and research behind these arms that they said definitely needs to be addressed. So when I was reading through it, I really liked how they went in depth about how they modified like both the myoelectric arm and the body powered arm. Like there's like pages about how they changed it and like why they changed it and what like these needs were. So they were documenting all these changes that they wanted to make. And then they also like included recommendations regarding this about how the field should be changing. And then when they were like doing their analysis of like the different activities, they had a mounted camera on the socket, which let them kind of get this like almost first person view about what the hand was doing. Which that's great because it lets them see. So if there's like issues with grip, they're very apparent. Cons, like I said, the body powered prosthesis was fully customized. Sure, a lot of it was covered by insurance, but he also paid out of pocket for it. And then there was funding coming into the university he worked at. So this isn't necessarily something a regular user would have access to. So it's not necessarily that applicable to your general kind of population. Like they're not going to get this on. It was also a case study of an expert user. This guy's been an amputee for a very long time, so he has a lot of experience working with prosthetics. So not necessarily like, oh, someone who's just received an amputation is going to take a lot away from this. And also the data collection and training times were kind of vague. Like they're like, this guy's been wearing like both of these types of prosthetics for like years, so he knows how to use them. And then we collected data over like 12-hour shifts for a couple of weeks, but there was no like breakdown of what happened on each of these shifts. They just said like, hey, he went to these different scenes like this number of times, but no actual like discussion of how the data was collected and grouped. They just kind of like told you things. Then for my AI component, I asked Gemini if I was to be doing hard, heavy lifting, what sort of prosthetic hand would I want? And it did recommend a body powered one. It did though bring up heavy duty bionic hands, but like we just established, there's a lot of issues with bionic hands that have nothing to do with the actual hand itself. And it did actually have a little consideration for intensive work. It was like, yes, they're vulnerable. And I had to prompt it then and be like, hey, why does it not like sweat? And then it was like, oh, there's some problems. I also asked ChatGPT. Bestie was really chatty. I got this summary by asking it to summarize what it just told me, because it just gave me like paragraphs. And I was like, okay, thanks. But it also liked the body powered device better. And then it also had a little concession about the myoelectric devices not necessarily being great. ChatGPT also cited Reddit. Gemini did not. Take from that what you will. Anyways, so I did list some discussion questions, but if you have any questions, I will be happy.
I was wondering if the researchers found any thing talking about phantom pain among their participants with anything like that at all?
No, they didn't discuss phantom pain at all.
Okay.
It is a very large, I want to call it, like, it is an issue within amputees. But they didn't talk about it. They only had the one participant and he was the first author. So I guess he was like, we don't care.
Okay.
How common is participant observation studies of this nature, case studies, in prosthetic development and in this particular area? Maybe you don't know, but.
It's not super common. They actually bring up another, it wasn't a case study, but they brought up another study where they looked at farmers with prosthetic arms. And they were like, this was like the first time anyone had ever like in depth looked at like using prosthetic arms in one of these heavy environments with like the actual people. And they were talking a lot about how studies kind of ignore the kind of blue collar aspects that a lot of the users will be looking into because it's not as convenient.
Okay.
Given that the first author was also the one and only subject and that they built one of the arms they were testing, essentially, how do you think that impacts the validity of this study?
I think, I was a little suspicious at first, but when I tell you there's pages of this dedicated, my man was complaining a lot about how these prosthetics worked. He was kind of upset that he had to make his own from scratch, and he's just like, look, I had to make a prosthetic, the body powered one where I could just replace the hand. He's like, I couldn't get that off the shelf, and that just helped me a lot more, where I had to make this locking. But like I said, all the data they took was really subjective. I would have loved for them to actually measure sweat, or have some sort of substantial measure about the electrodes. They're like, oh, they're not working, but they didn't say anything about signal degradation or the kinds of electrodes that were being used. It was just a lot of this is my arm, and you're like, okay, cool. But they talked a lot about how they made it, which I thought was really great.
On that same note, it's kind of interesting that, you find that as suspicious that the first author is the subject, et cetera. But if you want to talk to an expert, who are you going to talk to?
Yeah.
So he's the best qualified to talk about it.
Yeah, and I think it very much feels like a passion paper where he wanted to look into this because it's a problem that he very specifically has. And he brings it up. He's like, yeah, nobody talks about forensic medicine with these heavy occupational environments because it's not pretty. I did censor one of their figures because I didn't want to just pop up a very bad cat scratch, if we're gonna be honest. Because it's messy, but as he was saying, a lot of occupational work is.
What you kind of alluded to it a little bit, but what would be some not subjective measures, but quantitative measures that you think could potentially be assessed in the field?
Yeah, I think if they actually put some sensors on him while he was working to collect sweat and just see how much that was actually being produced rather than, hey, did I sweat through 2 layers of clothing? Yes, no. I think that would have had a lot of oh, okay. And then you could directly measure the amount of sweat produced compared to that. I also, like I said, would have liked to see the actual sensor readings or something about the sensor readings from the myoelectric arms. Cause like he was working with industry while doing this too. I feel like with the amount of collaboration and customization he was doing, it would have been helpful to just see like what the sensors were doing, especially as he was talking about them failing. And like sure he had some like objective measures, like kind of like the grip strength tests and the weight, but there was no like real like data in regards to, but I think there's a set of sensors that aren't like huge. Like I don't think he needed to do motion capture. He didn't need anything as intense as that.
I kind of interpreted this paper as like someone who was almost wanting to write a memoir about their experiences,
Yeah.
but decided that the best way for them to kind of get to people who could maybe make a change in the field was to write it as a scientific paper.
Mhm.
And so then they did the easiest data collection possible for them to make it a scientific paper, which I think there's a lot of value in the paper in the fact that it's his perspective on how these actually work, which is super critical to all of our research in actually working with patients who would benefit from a device like this and how would they use them in their daily life, which is maybe very much missed in this field. And so I think in that way, it's super valuable of looking at this personal experience using these devices in the real world, because it is true that that's not as well used. But in terms of actual data collection, I'm not sure that's the most reliable.
So the response was like, did I sweat? Yes, no. I was like,
Yeah, exactly.
This kind of maybe a question. I see Melissa. I don't know if we have other, yeah, we have some residents. Isn't a case study approach pretty common in medical journals? Don't you occasionally have case study articles?
We do on one token individual, so it's almost like anecdotal.
Right,
Right.
because more like a patient story for
Mm-hmm.
a particular, sometimes unusual or difficult cases. So I,
The history of that, like how that's presented is the very first paragraph is like 43-year-old man comes in with blah, 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 blah. He presents blah, 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 all this stuff. And then you go into the background of like what your theory of the diagnosis is. And you talk about the background, what is socially, like what is the acceptable method of testing, all the stuff that's evidence, like what is currently in practice. And then at the end, you talk about their labs, their objective, and then your conclusion.
where I'm kind of headed is this, there's a long tradition, like in psychology, some of the early founders of the field extensively use themselves as research subjects. And it's kind of good practice to be your own subject in any study protocol, but the power of a case study can be quite strong. Like, do you really need more than one person to show that the one creates severe blisters that take 6 weeks to heal? I mean, maybe 3 people would be enough, or 10, but at a certain point, the case study pretty dramatically demonstrates that the one technology is inadequate for heavy work, and maybe it's accomplishing his function. You know, we're all talking about it, and there's engineers in the room, and so yeah, I thought I'd just bring that up. A case study as a research design or tradition is out there in some disciplines, and sometimes you don't need more than a few folks.
Yeah, he also had like a lot of points I wouldn't have even thought about, like especially when he was talking about like the passive device, the body powered one, where he was like, I literally couldn't get any of these parts. And then like when he redesigned it, like the cabling, he changed it to an easier cable that you could just like order offline. Cause like a lot of the problems he was having was like, nobody has the parts in stock. So he had to like wait weeks and weeks and weeks for them. And it's just one of those like smaller things you don't necessarily consider when you're looking into just like research design.
So I love what you're talking about here. I think in terms of case studies and that sort of thing, the interesting thing about case studies is they're present in nearly every discipline, frankly, because there are situations that just don't happen very often, and we can't replicate. We cannot shove a tapping rod through someone's head on a regular basis. So it's not something we do, but there's a whole bunch of case studies and really great work done by early psychologists about what happens when the frontal lobe of a person is ripped out of their head, right? Or compromised in certain ways and so forth, right? And so we have to recognize this is a legitimate research way of doing research, particularly for situations that are are really hard to, or unethical to create,
You're
right?
saying we shouldn't cut people's arms off?
Yeah, we shouldn't cut people's arms off.
I don't think
We
you would
can't-
pass
we can't do
IRB.
that. We can't throw tap rods through people's heads, we can't, but we do need to, when those things happen, it's important for us to learn from them.
Yeah.
Right? So and there are certain questions we can answer with a case study that we cannot answer with a randomized controlled trial, or we cannot answer with a cross-sectional design, and that's perfectly fine. And so I think I wanna make sure we recognize that, yeah, the external validity of this is garbage, right? But that's not the point, and that was not the research question, right? And so if your research question and your purpose is not to generalize to a large population of amputees, but to understand the experience of a person who's doing a particular type of job, this is brilliant. Right? So you gotta recognize those differences and do the research do the study that will answer the question.
Yeah, no, I thought it was fascinating, like there was a lot of stuff, like I didn't talk about how they were talking about like hand covers and stuff.
Yeah.
To like add grip and how like different hand designs impact that.
Yeah.
Long story short, if you've ever seen Formula One, it's the same as the wheels where the softer ones have the stronger grip, but they degrade faster. And they had like a lot discussing that. It was just all these like little details and he was like really thorough about it, which I thought was very good.
I guess to kind of talk more about like mitigating the issues, like your first question, I think you would need to open that up to more subjects. Maybe you can expand on this too and your thoughts, but I guess really understand and like how to mitigate the issues with sweat. Maybe you can explain to us more how exactly the body power perhaps work, and what ways are they, obviously they're wearing like more equipment that maybe adds to the problem with sweat, but in what ways are they moving their body maybe differently to accomplish these tasks that maybe add to the problem?
Yeah, with the body powered arm, they didn't see sweat as like a control issue in the sense of the myoelectric one. Rather, sweat was causing like a lot of the friction stuff to happen. Because when you're wearing a prosthetic device, you have this socket, which I brought up, it's just the hard stiff bit that attaches the prosthetic to your joint. But there's also a bunch of liners, which can be made out of a bunch of things. Like you have fabric ones, you have gel ones, and they go on the inside of the socket and they kind of cushion your residual limb and keep the socket in place at the same time. So liners are a very complex issue. He talks about it and how he was wearing liners that weren't comfortable because of the shape of his residual limb. But since you just have a bunch of layers, it causes a lot of sweat. And it can start rubbing and moving because it's not held as securely in place as it would have been, which causes a lot of the like friction rashes. The control scheme for the body powered is, like I said, you've got a little cable that starts at the hand and it runs up to your shoulder. So as you move your shoulder, it adds tension or it tensions the cable. So you can either open the hand with the tensioning or you can close. There's two varieties of hands you can get that do either of those things. It's kind of like scissors. So as you move your shoulder, it'll open and close the hand. That's how it works. It's simple. There's a reason that they've been popular since 1912. The problems he was talking about in regards to like actually the harnessing was a lot of the shoulder problems because of how to get like the harness to attach onto you and like be able to do that tension without kind of pulling on your neck muscles and causing stressors that way. So in that regard, it wasn't really a stress issue. It was mostly just to do with the skin issues he was having down.
So you mentioned in terms of like time until they were unable to continue using the prosthetic device from like physical perspectives of skin abrasions and things like that. Did they discuss at all the cognitive aspects of using the myoelectric hand or any of the limitations of using that side or just the like physical skin socket?
It was actually cool because he discussed it for both hands. So with the myoelectric, he was talking about how they put the two electrodes on you. They use two, so one on, but basically they use two electrodes and you can get a lot of different signals, hence the like torso bending. And he talked about how it wasn't as like intuitive as the body powered one, which he found, you know, you can put it on and you can like open and close it, but for both, he was talking about how it takes a lot longer to become like an expert in them. So you could wear both devices and you'd get the body powered one faster. Like you'd be like, oh, I can open and close it, but for both devices, there is a long period where you're not an expert and you're gonna be learning a lot about it. I think he liked the body powered one better, so he talked a bit more about that. But with a lot of the training, he was just saying that like he could open and close it. It was just once he started like moving his torso around, it was causing the hand to like freak out. So he had to like train himself to move his upper body in a different way, so it wasn't causing these problems, which he didn't call it annoying because it's a scientific paper, but so.
All right, I think we're at time unless there's any final thoughts.
Thank you.
I used to work on an angle.
Like I said, I like my own.
If not, I could have Joe. Hey, what's?
Let me,
Okay.
when I go through this way, I'll come
Okay.
with it.
No worries. Thank
But I
you.
am next to
Oh, I'll send him from.
Oh, yeah, speaking of that, I tried to connect with you.
I thought I hit accept.
Oh, maybe I haven't
Oh.
looked since then.
Yeah.
Have you looked at it? That sounds like. And I see like a set of people that I haven't thought of. Really, like, holy shoot, like, connect with all these guys.
Smiley?
I've
never heard of. Yeah.
Oh, really? That's so funny. So
Yep,
weird.
just fire away.
Like, especially with.
Hi, everybody. My name is Tim. I am a first year PhD student at the HGN Lab for Bionic Engineering. I'm also a first year trainee here at the Rocky Mountain Center. So it's been awesome getting to know everyone through Journal Club and Nora and stuff. And I'm excited to get to know you better over the next several years. Today, I am presenting on a problem near and dear to my heart, and being in a room full of grad students and academics, I would imagine near and dear to many of your hearts as well. Walking with coffee, why does it spill? So it's like a super common trope, but also one that I think holds true, where like, you know, you're in a rush to get somewhere, you got your morning coffee and it ends up all over the floor. So why does that happen? It's actually, the premise is kind of silly, but this paper is actually really detailed. And the way they go through it, I think, is really interesting. So hopefully you guys think it's as interesting as I do. Yeah. So the purpose of this study is to investigate why coffee spills when a person walks with a cup. They did this both with experimental data, and they also did it with mathematical modeling, which I thought was really cool. So some background: the natural sloshing frequency of liquid in a cup depends on the radius and then the depth or the height. And coffee mugs, there's some variation, but for the most part, they're all kind of the same radius and the same height. And so that's what decides the natural sloshing frequency of the fluid inside of it. The human step frequency obviously ranges depending on a person's biomechanics and anthropometrics, but it's typically between 1 and 2.5 hertz. I should mention that, the sloshing frequency for a typical mug, this study characterized to be about 3.5 hertz. And then, I'll get more into this later, but they, realize that the sloshing in a cup is like this back and forth motion when you're walking. It kind of sloshes this way, but it also sloshes side to side and then also spirals. So there's kind of a bunch, but they decided that the anti-symmetric mode dominates the sloshing, which is anti-symmetric is when you're walking this way, it's this kind of like sloshing back and forth in the direction that you're walking. So about the study, it was a single participant walking in a straight 4 to 5 meter path. They had various cup levels that was characterized by spill angle. So I have a figure on the next slide that might make spill angle a little more clear, but it's essentially like from how far they filled it up, what angle does the coffee have to reach before it's going over the edge. They tested a range of speeds from 0.5 meter per second to 2.5 meters per second. The instrumentation was a 100 FPS camera, and they did all the measurements and stuff like that using image analysis in MATLAB. They had 2 conditions, which is the participant focusing on not spilling or unfocused. So there's kind of this like, oh, I don't want to spill, or it's just like I'm going somewhere. And those are the 2 conditions. The methods, so this kind of shows this guy walking. They did all their analysis only in this XY plane. So they justified it a little bit, but mostly it's just because the sloshing this way didn't play a huge role and their velocity in that plane didn't play a huge role. So all of their analysis was done in this plane. This is kind of the spill angle I was talking about. So if they fill it this high, the spill angle is like, you know, whatever that is to get over the edge. And yeah, so we had this person walk with a cup, and then MATLAB decided how fast they were going in that direction and took a bunch of measurements along the way. Yeah, and then they recorded the number of steps it took until they spilled. And they also characterized the relationship between the maximum acceleration and the average acceleration. So I'll get into that a little more in a sec too. But yeah, these are kind of two metrics they looked at. Most importantly was like, yeah, the maximum acceleration. So they, this is going into the mathematical modeling methods. So they modeled it as a four spherical pendulum, representing the first antisymmetric mode, which is again, which is that kind of back and forth sloshing if you're walking this way. They derived motion using like kinetic and potential energy. They defined the forcing function like this, and it's kind of like a really complex looking equation, but really all it is a sine wave, you know, typical sine wave of a certain amplitude and oscillating at a certain frequency. And then they introduced a bunch of smaller sine waves to represent uneven terrain and perturbations and kind of just that natural variation that happens while you're walking. So that's like the noise. And they characterize that randomly. And then, yeah, yet again, both the mathematical model and the experimental model is the same thing. The number of steps to spill versus the acceleration ratio, which is that max acceleration compared to the average acceleration. So now on to some results. There were a lot of kind of interesting things that came from this. So they found that the frequency that someone is walking with almost exactly matches the frequency that the coffee was sloshing with. One thing I should have mentioned, they had a sensor in the cup that could measure the sloshing, super simply measure. It was just like a yes or a no. Yes, there's coffee here, or no, there isn't, but they were able to derive the sloshing frequency from that. And they found that it correlated almost exactly with the frequency that one was walking with. They also realized that the amplitude of excitation increases with walking speed. That's you know, maybe intuitive. The faster you walk, the more it sloshes. They found that the maximum acceleration was kind of a good measure of this. Well, this plot explains it very well. So there's kind of these two regimes in walking. There's this kind of rapid acceleration, and then you reach this, you know, the speed that you want to go at, and you stay right around there. And so they realized that that maximum acceleration that happens right when you first start walking is the best measure of this initial displacement. And then while you're walking, that the harmonic motion kind of makes it worse and worse and worse and worse until eventually it spills. So they found that the initial acceleration was lower in the focused regime, which kind of also makes sense. If I'm trying not to spill, I'm going to kind of like do this rather than like, oh, I'm on my way. You just start heading. And then they found that the yeah, okay. So this is kind of this motion in the Y plane they're talking about, which is up and down. They did notice this is just kind of happens with your steps naturally. You kind of go up and down. So this was less in the focused regime. It was present throughout, but they also decided through their mathematical models that this motion did not play a very large role in the sloshing, and it was more the forward-backward motion. And what the results ended up being, which was really interesting, is that the like natural frequency that a typical mug, like the natural frequency that that coffee sloshes around in a typical mug was like, yeah, 3.5 hertz. The walking frequency is almost exactly half that, which means the two frequencies are commensurate. So your walking frequency is exactly half of the resonance frequency of this coffee. And so it tends to, as you go, like make it worse and worse and worse. It keeps building upon the displacement rather than fighting it or not affecting it all. It's this kind of feedback loop. And so it's just kind of interesting that that's the pace we walk at and the frequency with which we take steps tends to be the perfect frequency to kind of make these excitations worse and worse and worse. And then this plot I thought was kind of cool. this plot shows on the x-axis, it's that initial acceleration versus the average acceleration. So how fast is that, like an initial jerk when you start going? And then how many steps to spill. And so it's the slower it is, the more steps to spill, but you still spill. It's like almost like spilling is like guaranteed if you fill your cup past a certain level. So that's what each of these lines is how full the cup was. And so it's almost like it's guaranteed because of that resonance frequency phenomena where like the excitation just get worse and worse and worse. So there is a level to where like, you know, because it's exponential, it's like a million billion steps, but spilling is almost guaranteed, which I found really, really interesting. But yeah, so that initial acceleration plays a huge role in how quickly you spill. And then obviously fill level also plays a huge role in how quickly you spill. And it gets to this point, which is where essentially you're just at this, like you accelerate so fast that that initial perturbation just immediately you spill. And so it's kind of this exponential relationship until that point. So yeah, lots of interesting things, I think. Make sure I'm not missing anything. Cool. Some other interesting things were like walking, let me see. The like pace with which you walk actually varies less when you are walking faster, which I thought was interesting. It's kind of, you would think more slow controlled walking would vary less, but that is not the case, which is kind of a secondary finding. Another, like there's a plot that I didn't put in here that I wish I did, that if you have the paper in front of you, it's figure 4A. It's not like super interesting, but it does show that difference in focused regime versus unfocused regime and how long it takes to spill. It just kind of aptly puts that, yeah, if you're unfocused, you tend to spill quicker than focused. Cool. All right, so some strengths and weaknesses of this. Yeah, so some strengths and weaknesses are, I thought it was cool that they did both mathematical modeling and empirical modeling, and they both agreed, they both said the same thing, which is that initial acceleration plays a huge role, fill level plays a huge role, and also that the sloshing frequency is like almost perfect. It just creates a perfect storm of you're gonna spill your coffee, it's just a matter of when. And the results also kind of match intuition in the sense of like, yeah, the quicker I accelerate, the more you spill. And you know, it all kind of seems like if I were to try to think about why I'm spilling my coffee every morning, the conclusions of this are the same as the conclusions that come to intuitively. The limitations are it was a single subject. They did address this limitation by saying that the frequency with which people walk does not depend much on their height or anything like that. But it would have been cool if they showed that by maybe having like, even if it was just 2 more subjects with like slightly different anthropometrics, and they say, look, these people were different sexes and different heights and all this, and their stepping frequencies were still within this range. I think that would have been really great to address that, but they didn't. They still stuck with their single subject. They only did 1 trial per condition. So each walking speed and then the focused versus unfocused regime, they only did 1 trial and then moved on. I think it would be cool, you know, they talk about how fluid mechanics and harmonics and everything tells us that the sloshing frequency of a mug depends only on radius and height. But I think it would have been cool if they experimented with different mugs and kind of characterized that effect. I think it would be really interesting. And my first read through of the paper, I had a kind of a hard time. In my opinion, they used the variables and they used the coordinate plane way before they defined what the coordinate plane was. And so I had a hard time following it. It kind of took a few read throughs before I understood where they were going with that. So AI's role in this was helping me find the article. So I prompted ChatGPT with saying, like, help finding a peer-reviewed research article. It's kind of this long thing, but I basically gave some examples of some previous presentations that I've seen here that I thought were interesting. And I said it has to be, you know, related to occupational safety, but I'd also like it to be interesting and fun. And I think it did a great job of finding a paper that is interesting and fun and moderately related to occupational safety.
They all need topic.
So kind of wrapping up, spills, you know, the conclusion of this and the takeaways from this study are spills can be prevented by accelerating slowly, which is boring. I got you can fill your cup less, which is like definitely a non-negotiable. No way by putting less coffee in my cup. You can augment the cup size to move the resonance frequency away. But the formula that derives this, you have to kind of like really change the cup size a lot. So it's like you have to be walking around with like a comically wide mug or a super tall mug or something weird. There's also interesting engineering solutions that the authors brought up, like baffles, which are used in like rocket ship fuel tanks they use to stop this sloshing. They add baffles. There's like flexible cup walls, which is cool. Or you can just put a lid on your mug. Problem solved. Yeah, so I think there's some interesting discussion. How could these findings be used to improve workplace safety? You know, do we mandate baffles in people's mugs if you're walking around with coffee? How could the study be improved? I think there's a number of ways. And then one other interesting thing is like the fact that spilling was reduced in the focused regime. The authors talk about this, and I thought it was interesting. Is it like a subconscious kind of control method of like you're looking at the sloshing frequency and your brain does all these calculations of like, oh, if I walk at this frequency, I'm not walking at that excitation frequency that makes it get worse and worse. Is that intentional? Is there a bunch of computation going on? Or is it literally just like the slower acceleration and it just happens to work out? So, yeah, I'd love to get some thoughts and questions.
So I'm surprised they didn't look into viscosity related metrics, you know, because as soon as you start adding sugar or cream, the nature of the liquid changes, right? And so if it's 100% black coffee, then I think most of this probably applies. But, you know, if you like these other things or the other additives, then the coffee viscosity changes and the spillability of the mug that you're carrying it in changes.
That would be really awesome to see a mocha character.
Right? What's a mocha? What's a latte? What's a cappuccino? How does that change? And maybe someone who is prone to spilling should be switching up and adding some cream.
Going off that, not that I exclusively drink lattes. However, I exclusively drink sugary lattes. And whenever you fill up the cup with the foamy milk afterward, it normally goes over the top of it. So there's like some element of almost like surface tension going on. So did they like discuss like how fast you need to walk to break that surface tension and just cause it to go like everywhere?
So they enjoy real coffee, which is black.
Say you don't want the extra sugar and stop pretending like it tastes good.
So no, they did not discuss any kind of filling, because I don't believe that one.
Sorry.
So how did they determine the sloshing frequency of the contents of the mug?
Do you mean like the resonance frequency, that frequency that excites it, or like what it actually was during experimentation?
Maybe both, because they picked a number, right, and they used that for their mathematical model.
Yeah, so
Intuitive to me that there's a single value for that.
So they picked a value with their mathematical model through some complicated formula that I don't know, but exists in like this kind of fluid mechanics harmonic frequency world that is derived from the viscosity of the fluid and then mug dimension, so how wide it is and how tall it is. And so yeah, they calculated that given a bunch of fancy equations and probably, you know, just characterize like a typical mug, which of course there's some variation, but they did address this, but they also mentioned that within like what a reasonable mug is, this frequency doesn't change much and that the effect still exists. And then how they found the actual frequency is they had like a little diode that basically just sensed whether liquid was covering it or not. And then you can see kind of this yes, no, yes, no, yes, no, and that's the sloshing.
Just a quick comment that with regard to applications that are pretty common for managing liquid physics, liquid transportation in large commercial trucks, those trailers all are typically baffled so that the liquid isn't causing instability in the truck. So you don't have to go to outer space for the baffling to be applicable to safety.
So in fact, when you look at complex humanitarian emergencies, like when you talk about large refugee camps and they have to transport water, before the baffle trucks, that was the largest mortality and workplace injury, was transporting water. Yeah.
Yeah.
So there you go.
Baffles. Now I want one in my coffee cup. I want a baffled coffee cup.
So I know the purpose of this wasn't to like measure like frequency of spillage exactly, but I guess my question is like, did they stop measuring once the liquid spilt over the side, because theoretically, if they kept walking and the volume of their coffee mug went down, would the likelihood of spillage also decrease?
Interesting. I think that is the case. Hopefully this person is stopping for cleaning up their mess.
Yeah.
Yeah. So they did stop both the mathematical model and the experiment. Both the cutoff times were as soon as the first drop was.
Okay, yeah.
But that would be interesting to see if they had continued walking, you know, because there is that like excitation of it does continue to get worse, but also the spill angle increases, which decreases likelihood. So that would be really cool to see several more steps after.
Did anybody else find it odd that they mentioned baffles but not lids?
Yeah, that- I found that odd too. Honestly, truthfully, because I like, you know, was reading the paper, I was thinking of baffles and all, and like flexible cups and all this. And it was actually, it took a postdoc in my lab who said, why don't you just put a lid on it? Yeah, it was cool like this, so.
More deliberate, come on.
Jump the car on the top.
Can you also change the shape of the mug, like same height at the top and at the bottom, but just round it over in the middle, shouldn't that also change how the liquid sloshes?
Yeah, true. Could be, but then like when you're drinking it, you know, there's a theoretical minimum amount because then it wouldn't make it over that lid when you're trying to drink. So then you're leaving coffee in the cup, which is again non-negotiable.
Poor soul.
Yeah. Like drinking through a straw or something.
Do you think that, for example, in our lab, we have a large lab space and the coffee machine's all the way on one wall? Are people who sit farther away from the coffee machine more at risk of spilling their coffee then?
I would say almost definitely because you know, they characterize it versus number of steps. So if I have 3 steps, I'm probably safe. But like a whole 15 steps to my desk, I'm
Probably
spilling.
not.
I'm definitely spilling.
If you average it out over distance though, you're probably not.
True.
Do people spill their coffee?
I spill my coffee probably once or twice a week. So anecdotally, yes.
I put milk in my coffee, so no.
She changes the viscosity.
That's all you gotta do.
That's an engineering skill.
Yeah.
They're really kind of mutts, right, not people, so like, I'm just curious to see how it changes in terms of how you hold them on, like women's center mass is lower than men's, and I just wonder if just that change in kind of where it's held, or like the alignment of your mug with your body.
They did kind of briefly mention, but not explore, the fact that wrist stability and wrist rigidity plays into this a lot, because your wrist can kind of have this natural damping,
Yeah.
reducing the vibration from like your legs all the way to your mug, versus if you're really rigidly holding it, it all transfers, and so.
But if you hold it away from your body versus right next to it, right?
Yeah.
Very different.
Got a little like lever arm
I
and
feel
stuff,
like
and I think that would be cool.
Definitely.
And if you wear a white shirt, you're always
Yeah.
scared
Yeah.
that your risk goes up.
Definitely the wrist, yeah. The wrist should have characterized that.
Yeah. I thought it was interesting that they did talk about, like, they did justify this choice of one subject. They're like, oh, your walking speed doesn't change that much. But it does, actually. Men and women have different self-selected walking speeds because center of mass is different. Also, leg length does play a role in your self-selected walking speed. And in biomechanics, there's a huge debate about whether or not you should actually normalize walking speed and other outcomes to leg length, not just walking speed or weight.
Also, footwear. If
Yes.
you are wearing Louboutins versus
You
footballs.
are for sure spilling your coffee.
I thought that was really weird that they just wrote that off and they said like biomechanics states, that's like, they didn't even know like citation number, they
No,
said.
the lack of citation. is
Yeah.
concerning.
They said biomechanics states that step frequency doesn't change much. So it wasn't necessarily walking speed that they were talking
That's
about.
fair.
It was step frequency, and they said that doesn't change much with anthropometrics, but all it takes is a second subject with different enough anthropometrics to kind of back that claim up,
Right.
and they did. That would be cool to see.
Maybe just another thought, but I think we've all seen those like demonstrations where the physics teacher like swings the bucket of water around his head. I wonder if there's like an engineering opportunity or a business opportunity here where we can make like a pendulum, a coffee carrier, where you can carry the pendulum and it makes it really hard to spill the coffee.
Really hard to
Like
drink.
interesting.
Yeah, well, you just put the mug in there,
Oh, I see what you're saying.
right? And then you can hold the mug on this little
While you're walking.
pendulum.
Yeah.
Okay, that exists.
Oh, does it?
For like baby cups.
Oh,
yeah.
Like,
So we just need to
adapt that for
Gyroscope mug.
This was made in 2012. Has there been any follow-up studies?
No, one would hope that by now we have a gyroscope mug or baffled mugs
Do
maybe.
you have a PhD project?
I'm thinking about switching directions. I just gotta get funding, so if you know anyone.
Shark Tank.
Shark Tank. Any other thoughts or yes?
Okay, so if you were gonna design like an aesthetically pleasing, also usable anti-spill coffee cup, possibly with baffles or a gyroscope, what would be like, do you think baffles would be more effective than a gyroscope? Do you feel like, how do you make baffles aesthetically pleasing, like?
So I think baffles would be cool as hell just in general. Like, I think it would be more aesthetic than a gyroscope maybe less attention grabbing, but the gyroscope mechanism takes a bunch of like extra engineering outside rather than just some ridges in your cup. And then also you have to worry about like the longevity of it because as it moves around, any moving part is gonna wear down and degrade. Baffles kind of theoretically last forever. But I think the most aesthetic and like clean solution to this is a lid.
Take your bedazzle gun.
Yeah. A gyroscope would be an attention getter, I'm sure. Conversation starter. Yeah, or a string.
Just so you know, on Amazon, you can get a mug that has a baffled face. Right? The face is baffling, right? But not baffles in the mug itself.
It sounds like a market opportunity.
So
I am looking
just
for
thought
investors.
you should know. If you want a mug that looks like it's baffled, you can do that, but not baffled.
Well, I know how I'm making my millions.
There you go. There's a business opportunity.
I've just got an overall comment about both of the discussions for both papers today. Very good discussions. Everyone, thank you for participating. Getting to article choice, not that every article should be, that we present in Journal Club should be a somewhat silly-ish article, but give like the discussion element of it some consideration when you're picking your articles. Because what I find just having, been in Journal Club for many years now, the article itself goes a long way to determining what the discussion is gonna be. And sitting up there for 15 minutes trying to facilitate a discussion, a lot easier if you've got a good article that people are interested in. So obviously that should not be the only, factor that you're considering when picking an article. Do something you are interested in, applicable to your own research, all that stuff. But just good job picking 2 articles that people were interested in.
Thank you everyone for the fun discussion.